I am Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. Let me thank all the viewers and supporters for watching my videos and providing excellent suggestions. As per your request, here is a video on applications of exponential functions. So, we have carefully selected four different types of questions, starting from basics to where you will be using logarithms to find the answer in these application questions. In case you really want to learn from me, send an email on Global Math Institute. Our students are right there on the success path and doing extremely well. What you get from GMI is you get the top grades, you can master concepts and strategies, and innovative and creative solutions. That makes a huge difference. Now, let's look into the four questions which we are talking about. Here are four situations, real life situations for you, which are going to take one by one. You can always pause the video, answer these questions, and then look into my suggestions. So let's begin with the very first one, which is regarding a ball dropped from a height of 10 meters bounces to the height of 80% of its previous height. Determine the maximum height of the ball after 10th bounce. A very straightforward question here, right? So basically, if we consider this to be the ground and the ball which is dropped, let's stretch it a bit like this, it bounces to 80% of the position. Do you see that? It's kind of like this, right? So that is the situation. We are leaving the ball from 10 meters height, and every time it just goes to 80% of the previous situation. So 10 meters, 80% will be 10 times 0.8, right? So that is 80%. Now, in the next bounce, it will be 80% of the previous bounce. That means 10 times 0.8 times 0.8, and so we can write square here. So this is after the first bounce, right? And that is after the second bounce. As you can clearly see, that after second bounce, the exponent is 2, right? Sometimes you need to check this as many times. Students might do this mistake. So basically, we can say that the height after every bounce, let's say the number of bounces are n, will be the initial height, which is a0, times the factor, right? So we call this r and to the power of n, right? So in our case, we know that the initial height is equal to 10 meters, right? And the decay rate is 80%, 80% of the previous, right? So basically we can write this equation as equal to, starting from 10 meters, it goes 80%, 0.80 is the rate to the power of n. What we need to figure out is what is the maximum height of the ball after 10th bounce, right? So n is 10 now for us, correct? So we can write h of 10 after the 10th bounce will be 10 times 0.80 to the power of 10. Is that clear to you? Simple as that to begin with, but an excellent question understanding the concept, right? So that's where we are. And we are going to multiply 10 by zero point 0.8 to the power of 10, right? So 10 times this gives us the answer as equal to 1.07. So after the 10th bounce, that is going to be the case. Let's recalculate this. Zero point 0.8 to the power of 10, right? And we are going to multiply this by 10. It is always a good practice to check your answer, right? So it is indeed this much. So we'll round it and write 1.07. So almost 1 meter, right? So that is the maximum height achieved. So maximum height will be 1.07 meters after 10th bounce. Is that clear? Perfect. Now let's move on and take up the next example. So I hope the fundamental concept is absolutely clear, right? Question number two here is: a species of bacteria doubles every 5 hours. Find approximate growth rate, right? So here we are given you something which is doubling period, right? And what we need to find is the growth rate. Very interesting question indeed. How will you do this particular equation? Well, the number of bacteria we could write at any instance of time t as equal to, initially starting with some number, right? So let's say n0. And growth rate, it says doubles, right? Twice. So 2 to the power of, what is the rate? Every 5 hours, right? So we write t over 5. You get the idea? So t over 5. So if I put t as 5, you get the 5 over 5 is 1. So we are multiplying by 2. So initial amount gets doubled up. You see the base of this equation? So that is the general formula for doubling, right? So you write the doubling period here. So let me rewrite the general formula here. So nt will be equals to n0 times 2 to the power of t over d, right? D is the doubling period. Here I've substituted 5 in that case, right? Now the question is find the approximate growth rate, right? Growth rate we have to find. So how do you find the growth rate and what is growth rate? How are these two equations different? This is what we need to figure out. You get the idea, right? So the thing here is that growth rate will be, we know something that if t is 1, let's say if t equals to 1, in that case our number will be 2n0, right? So output n of t will be, let me rewrite this, right? So if t is 1, then n of 1 will be equals to n0 times 2 to the power of 1 over 5, right? That is what it means, right? After 1 hour. But think about t to be equal to 5. If t is 5, then n of 5 will be equal to n0 times 2 to the power of 5 over 5. And you can see that n of 5 after 5 hours is twice the initial number of bacteria. So we just tested that our equation is perfectly fine, correct? Now here is how we have to find the growth rate. We say let growth rate be r, right? So normally it is r percent, right? Growth rate is r percent, right? That this be the growth rate. In that case, our equation now becomes that n of t is equal to n0 times 1 plus growth rate r, right, to the power of t, right? Some time period t. Now we know if t equals to 5, then nt is 2n0, right? So we can write this as 2n0 equals to n0, 1 plus r to the power of 5. So if t is 5, then the number doubles from the definition itself. Why I did all this? Just to show you this is the logic behind it, as some students find it difficult to even understand why this is done like that, correct? Now we can easily find r, the rate of growth, and this value will be in decimals. We'll have to convert that to percent. Remember that, right? So let's rearrange this. And what do we get? We get 2n0 divided by n0 is equals to 1 plus r to the power of 5. Now n0, n0 cancel. So this is equal to 2. Is that clear to you? And therefore, we can write 1 plus r is equal to the fifth root of 2, right? So let's find the fifth root of 2. That means 2 to the power of 1 divided by 5. You get the idea? Fifth root of 2, which is equal to 1.1486. 869, right? So let me write 869 here. Does make sense? So 1 plus r is this much. What is r? Can you tell me? You can now pause the video and answer the question, right? So let's rewrite the solution. So we have r now equals to 1.1486 minus 1. So that means clearly 0.1486, right? So R is decimal value, correct? So what is the percentage growth rate? Times 100, right? So it is 14.86%. Does make sense. So the growth rate in this particular case is 14.86%. Perfect. So I hope you have understood the method. We could have gone direct in this particular fashion, right down like this, right? But here I gave you an explanation of how do we figure this out, right? I hope that really helps. Feel free to send an email to me on globalmathinstitute@gmail.com to learn more. Thanks for your time. Now let's look into the next two questions. Now, this is again a very important question, live application. A certain antibiotic taken 4 times a day reduces the number of bacteria in your body by 10%. Each dose. How many doses must be administered to reduce the bacteria population to about 5%, right? So that is what the question here is. Try to make an attempt to solve this. It says a certain antibiotic taken 4 times a day reduces the number of bacteria in your body by 10%. So when you reduce the number by 10%, then how many remains? 90% remain, right? You could think like this. But anyway, we could also write this as a decay equation. So number of bacteria here can be written as initial bacteria number 1 minus 10%. So 10% is 0.10, right? To the power of how many times? To the power of number of doses, we'll say n, right? So each dose, this is kind of important, and therefore we will see that 4 times a day kind of confuses you at this moment, right? You should know what is not important, what is important for the equation, and when to use the given information. So that is another thing which we are going to learn as we go through this particular solution, right? Okay, so we want 5% of the initial population. So what does it mean? So 5% of initial population, that is what it means, right? So which basically is 0.05 of n0, correct? So we want to find n when that is the final number of the bacteria left, right? So let's put this. So that means 0.05 initial population times initial population, and this is 0.90 to the power of n. Get the idea? Initial population get cancelled. So in many of these questions, you need not be given that these are the starting points. You get the idea? Normally, we even don't know about it, correct? But we know what is a safe level, right? So safe level is 5%. Okay, great, in this particular case. Now the problem here is that n is in exponent. How do we solve this particular case? Now that is kind of critical, and this is what we have taken this question for. So we need to take logarithms to solve. Is that clear to you? So we'll take log both sides. We say log of 0.05 is equal to log of 0.90 to the power of n. So log rules will apply. 0.05 equals to n times log of 0.90, and we can now find n as a ratio, correct? So n is equal to, let me change the ink here, n is equals to log of 0.05 divided by log of 0.90. Makes sense, correct? Use calculator, figure this out, right? So we have log of 0.05 divided by log of zero point 0.9. Is that clear to you? So when you do that, you get 28.43. You should do along with me and check your answers, okay? You should understand log to the base 10 I have taken and then got these values. You could have taken ln also log to the base e. Perfect. So 28.9, that means number of doses required is indeed 29, correct? So now the question is, uh, how many doses must be taken? So how many doses is 29 doses, right? So sometimes the question could be also how many days, right? If the question was how many days, we'll take this information into consideration. We are taking 4 doses per day. Do you get the idea? So we'll divide 29 by 4, correct? So 7 point something, correct? 7 is 28. You get the idea, 28. And then 10, so 0.05. So a little more than 7 days. So about a week, right? So I hope you get this right. So in a week's time, you will get over this particular bacteria by using the given antibiotic. That is what we are coming to conclusion with this. And what we need is number of doses 29, so probably 30 capsules, right? So this is how we practically see it. Great. I hope it's absolutely clear, right? Okay, let's move on to the very last question on this series of figuring out some applications based on exponential functions, right? So here is the last question. A yeast culture grows by quadrupling its number of cells every hour. There are 1,000 yeast cells at 11 a.m. At what time will there be million cells, right? So that is the question for you. How will you write this equation? So we are saying yeast cells number, right? Okay, equals to initial number times. It says quadrupling means 4 times its number of cells every hour, right? So 4 times every hour. So t over 1 we can write is quadrupling period. So every hour it is quadrupling. So t over 1. Do you get the idea? So quadrupling period is 1, so 4 over t. Okay, so that is what it is. 11 a.m. we are starting with 1,000, right? And from 1,000 we want 1 million cells. So let's put all this information. So now we get 1 million means 10 to the power of 6, right? 1,000, right? 1,000 equals to 1,000, 4 to the power of t only, right? Because the quadrupling time is every hour. If it was 2 hours, 3 hours, we would have written t over 2 or 3. Remember that part, okay? So basically, I should have written an equation here like this. Quadrupling period, right? So which is 4 times t over q, where q is the quadrupling period. But now, once again, this exercise, I would like you to use logarithms to find t. That's that's all right. So when I divide 1,000, 1 million by 1,000, I get 1,000, right? Equals to 4 to the power of t. Log of 1,000 is 3, right? We can write this as t times log of 4. Perfect. So we know t is, and this is 3, right? T of log 4. Because this is base 10, 10 to the power of 3, right? You can use calculator also. So now we can find the value of t as 3 divided by log of 4. So let's find this answer. 4.98. So approximately 5 hours, right? So in 5 hours, they will multiply and they will become a million cell, more than a million. You get the idea? So that is how we should be solving this type of question. So there was a variety of questions which we take, right? And two of them were using logarithms. So we introduced you how do we use logarithms to find the time, right? Basically the exponent. Log is inverse of exponential functions, and that is how it helps. I hope you find this journey of learning interesting and useful. In case you want to master this, you can always send an email on the address given. Feel free to write your comments, share your views, and if you like and subscribe to my videos, that'd be amazing. Thanks a lot and all the best.